Pass. That's it. How late were you? Pretty long. And so, it's pretty. 6 a.m. Yeah. Jeez. You guys get it done or no? Yeah, I got it. That's good. See you, Professor.
Hey guys, have a good weekend. Yep.
Are you gonna watch Suzume this weekend?
Oh, I want to.
What time?
I'm gonna be busy this weekend though, but we're planning, my friends and I were planning on doing it probably next couple weekends. But yeah, we really want to see it. It looks really good. Yeah, well, Shinkai's films are always really good. I didn't really like Weathering with You, maybe just because the main character was just really immature. But what was the one before that? Your Name was fantastic.
Oh yeah.
Love Your Name. Yeah. Of course, 5 centimeters per second made me cry like a baby.
I need to catch up.
Oh, you haven't watched 5 centimeters?
No, what I didn't. What's Your Name? Suzume. Suzume is upcoming because
Okay. Yeah, Weathering with You was okay. The main characters were kind of like kids, which, you know, if you go in knowing that they're kids, like I think people says it makes it better. 5 centimeters per second is very, very sad.
Is it good? I've heard good things about it.
5 centimeters, yeah, it's really good. It's
Is it on
definitely.
Netflix?
Oh, that I don't know. I watched it a very long time ago. I have it pirated on my computer. But yeah, it made me cry a lot. Sure.
Okay, if my
Okay.
sits in the back.
Yeah, no problem, no problem.
Okay, thanks.
I mean, there's only ever like 4 or 5 people.
Yeah.
I. Yeah, there's a lot of movies out. I know my a lot of my friends watched the Mario movie over the weekend. They said it was a lot of. My wife watched it without me. I thought we were gonna watch it together, and then Monday night while I was teaching, she's like, "I'm gonna watch the Mario movie." What the heck?
Dr. Chan, can you hear me?
Yeah, I can hear you, Ivan.
Okay, sounds good. Dr. Chan, I have a question.
Sure.
Can I ask now, or are you in
Yeah,
the middle of?
yeah. Now it's perfect.
So I know that EGME 520 Advanced Viscous Fluid Flow is going to be offered in the fall. Do you know if you're going to be the instructor?
Oh, I didn't even realize it was offered. I taught it back in 2020. Since then, another instructor has been teaching it. But I'm not sure.
It sounds good.
Probably not, because there are a lot of other classes that I could be teaching, and I also plan on continuing doing advising.
Sounds good.
But yeah, thanks for letting me know. I'll let my department chair know that I'm willing to teach it, but I don't know if he's going to give it to me or not.
Oh, I'm just asking because I communicate with a Dr. Mayoral very oftenly.
Oh,
And,
yeah. He's
I've
the
been-
one that taught it last time. And
Yeah,
so-
I really want to take that class, just so, because I've taken all the other classes similar to it, and I feel like that's the only, if I take that class, I get a well-rounded education here. So I'm,
Yeah. No, it's a
um,
good class. It's a good class.
so I inquired with Dr. Mayoral, but someone has recently told me that you also teach it. So I was just wondering, just so I
Oh, I
could know
see.
what to expect.
Yeah, it depends on, you know, it depends on kind of, so it's the department chair that kind of decides who ends up teaching what class, just because he's trying to balance kind of a lot of things at the same time. It could be neither of us, and so it could
Yeah,
be.
sounds good. I'm
could be-
familiar with, I took in classes with him also, and he's also a great professor. So I was just out of pure curiosity, I was just asking.
I see. Yeah, no, I mean, whether I teach or he teaches it, it's going to be a great class. So yeah, definitely recommend it.
Definitely, I'm gonna take it. Sounds good, sir.
Yep.
So I guess I have another follow-up question since you have taught that class before.
Sure.
I know that it may be completely different if Dr. Mayora teaches it, but from your past experience, is that class because advanced in Visit Flow was there was a lot of MATLAB in there. Is EGME 520 also when you taught it, is there also a lot of MATLAB or is it gonna be hand calculations or a
Personally,
mixture of both?
Personally, I teach it without any MATLAB.
Oh,
I focus
interesting.
a lot more on the conceptual side. I teach it very similar to like a classical fluids course.
Interesting.
So I don't have any applications. I don't have any coding or MATLAB or anything like that. So we focus
I
just
see,
on the
I see.
theory and the hand calculations. But
I see.
yeah, I can't speak for Dr. Myra.
Yeah, I understand. I understand. I'm just trying to gauge because that's gonna be my last term, and I just want to know what to expect my last term so I could plan everything accordingly. Because as you know, being a college student, the last term it's a very hectic term because you're trying to balance all these responsibilities out.
For sure, for
But
sure.
I don't want to waste any class time, so I'll let you get started.
Okay. Yeah, we can definitely talk after the class too. Okay, all right, it's 7 o'clock. Let's go ahead and get started. All right, so good evening, everyone. How's everyone feeling today? Doing good, doing good. Tired? Yeah, I'm still recovering a little bit from my extreme hangover from over the weekend. So I was a little bit out of it in the last class, but hopefully I can pull it together for this class. So today we have a fun activity. So this is a fun one. You may not think so because a lot of the activity today you're just going to be sitting around doing nothing. But under the hood, there's a lot of really cool stuff going on, just like we talked about on Monday, right? So we're going to be learning about design optimization today, and we're going to learn how to set that up within ANSYS. Okay. All right, and so kind of the situation is like this. So we have this kind of part. I call it a kind of a triangular plate or triangular shell. And what we want to do here is we want to optimize the dimensions of this plate such that we optimize better. So we kind of minimize the deformation. And we minimize the cost of production as well, okay? All right, so you guys know the drill at this point. So if you go to our course website on Canvas, you can go to assignments. The latest assignment here is activity 6, design optimization. And so you can download the instructions, and you can download the CAD file that's needed for this. And we're gonna open that up within ANSYS, okay? And just like any other activity, I'm gonna go at kind of a somewhat slower pace just to make sure everyone can catch up. But feel free to kind of read ahead in the document and jump ahead if you want, and just kind of wait for me. Okay. Okay, and so because the optimization, it does take a little bit longer, and I am having you do a little bit more extra stuff at the end. I'm giving you guys a couple more days for this, and so the due date for this activity is going to be next Friday, so Friday, April 21st, 2023. Okay. Next week we have a little bit of a break too, and so I know we did back-to-back activities last week and this week. So next week we don't have any activity, and so that's why I'm giving you a little bit extra time for this week. Okay. Any questions before we get started for today? Okay. All right. Oh,
are there certain units you want us to use? The units are listed in the assignment.
Just be consistent, and so as long as you're consistent, it's you can use whatever units that you want.
Sounds good.
Okay. All right, so just like I said, go ahead and download the CAD file, open up ANSYS Workbench, okay? And in kind of a nod back to our old activities, we're going to go with static structural this time. And so from the workbench here, you're going to take static structural, you're going to click and drag it over to the workspace area here. Okay. And then you're going to right click on the geometry and you're going to import the shell. Okay. And so the name of the model is triangular shell. Okay. And just for cost's sake, and so the original geometry for this activity actually was a kind of a normal solid type geometry. But it is very thin. And so I went ahead and converted it to a shell for you just to make the simulation a little bit faster. Okay. And so after you've imported the geometry, let's go ahead and open it up within Design Modeler. And so right click on this geometry here. And you want to open it up in Design Modeler. It should be the default because this part here was made in Design Modeler. But in case it's not the default, make sure you click this one and not Space Claim and not the other one that we've forget the other one already. But we're gonna open it up in design mode. Okay. Okay. And so the reason we're opening this up in design modular first, we're not making any changes to the geometry, so we're just leaving it as it is. But we're letting ANSYS know that ANSYS is going to have the ability to change this geometry, based on whichever parameters that we set. Okay. Because if you remember from our discussion on Monday, whenever you're running an optimization, you have to specify what your design variables are. Okay, so you have to specify, which variables that you're going to allow ANSYS to change throughout the optimization process. Okay. Okay. And so for this geometry here, the dimensions, the variables that we're going to allow ANSYS to change are going to be the dimensions of this plate itself. Okay. And so in design modular, you're going to go click on this sketch right here. Okay. And so you're going to expand surface sketch 1 and then click on sketch. Okay. And if you go to the bottom left of the screen, and let me make mine a little bit bigger just so you can see. Okay. If you go to the bottom left-hand side of the screen, you'll see that there are various dimensions that are being defined here. Okay. And so these dimensions here basically define the geometry of our plate. Okay. And I'm trying to see, is there a way to kind of see where these are? And so if you click on the geometry, or if you click on the dimensions, you can kind of see what they are. Okay. So a lot of them define, how big the part is, how big the radius of curvature is, the distance between those plates. Okay. And kind of the width of the plates as well. Okay. Okay. And so what we need to do at this point is we need to specify which parts of this or which dimensions are we going to allow the geometry, or are we going to allow it to change? Okay. And so later on in the activity, I'm going to have you experiment and try out different dimensions. But just so that we're all on the same page for this part, we're going to specify H4 as a parameter, okay, as well as R5. Okay, so these two parameters right here. Okay. And so to specify something as a design variable, what you're going to do is you're going to see, if you look at each of these dimensions, there is a check mark next to it, right? Or what it looks like a checkbox. Okay? So you're going to click on that checkbox. And so by doing so, you're going to put this P next to that parameter, right? So we have this PH4. And so what that P basically tells you is that that is now a design variable. And what you'll notice too is that, after you click on that P, this new window here is going to pop up, asking you to define a name for that parameter. Okay. And so, you can stick with the default name. That's okay. But usually when the program gives you the opportunity to name something, usually it's good to name it something that's going to be useful for you to remember later. Okay. And so in particular, this H4 parameter here, this defines the width, or this defines how much distance there is between the edge of the plate and this inner triangle here. Okay. So I'm going to give this a name, and so I'm going to give this the name width, okay? Just so that we know later on, what this parameter is referring to, okay? Okay, and so you can go ahead and click OK. And the other parameter that we're going to set here is this R5. Okay, so we're going to click on the checkbox next to R5, and we're going to set this, and then we're going to call this one the fillet radius. Because if you look at the figure here, this R5 defines the radius of curvature for this fillet right here. Okay. And so after you've named those two parameters and after you set them as design variables, we're going to click OK. Okay. And then from here, we're going to move on. Okay, and so of course, another thing that you can do is you can specify more design variables here, and that's certainly possible. But remember, if you remember from Monday, the cost of an optimization, or how many simulations that you need to run, it scales very hard with the number of parameters that you put. Okay, and so going from 2 to 3, is actually a very big increase in cost, and then going from 3 to 4 parameters is an even bigger increase in cost as well. Okay. So you want to be careful with how many design variables that you put, unless you have a lot of time on your hands, or unless you have a very powerful computer. Okay. And so just so that we can finish the activity within the confines of a single lecture, we're going to stick with 2 for now. But then on your own later on, I'm going to have you try with 3 and see, you know, how many simulations that takes. Yeah. So when you rename it, it occurs when you click on this P. Yeah, so a new box is going to show up that's going to allow you to name it. It's not going to rename the dimension itself, but it's going to give a name to the parameter, which is going to show up later on. Yeah. So it's still going to be called H4 and R5, but then internally the parameters are going to be called width and fillet radius. Yeah. You'll see in a bit. Yeah. Okay, question in the chat. All right, so far we've just made H4 and R5 as design variables. That's correct.
Dr. Chan.
Yep.
I just want to get a clear understanding of the semantics. Can you please describe the difference between a constraint and a parameter?
Yeah, so we haven't gone to constraints yet. But a constraint is basically a limitation on a parameter. And so what we defined so far, these are parameters, right? And so we can see the default, you know, right now this H4 has a value of 30 and this R5 has a value of 10. And so what's going to happen throughout the optimization is that ANSYS is going to modify these. And so it's going to change our H4. Maybe it's going to change it to maybe like 27.5. And it's going to change R5 to like 11 or something like that. And it's going to run a simulation. Right?
So our parameter sets a range, and our constraint has to be within that range. Is that the way to think about it?
So you'll see constraints later. So we haven't gone to constraints yet. But what you'll see later on is that, you know, once, you know, ANSYS is going to tell us, ANSYS is going to say, you know, I see that you've defined these 2 parameters.
Yes.
And so it's going to ask you, what are the constraints for these parameters? And so, for instance, we're going to say that H4 can only be between 25 and 35. So that 25 and 35, those are the constraints for parameter H4.
I see. Sounds good, sir.
Yep. All right, any other questions on this part here? Okay, so now that we've set these as parameters, we are good to go. So we can go ahead and close Design Modeler. Okay. And so after this, the only thing that you should have open is ANSYS Workbench. Okay. And so if you'll notice, you know, one thing that you should notice right away is that we have a new box here called parameter set. Okay. And so this box here is keeping track of all the parameters that we've set so far. Okay. So far we've set 2 parameters, and so we set basically two design variables, which is the width and the fillet radius. Okay, and so this is where the names kind of come up here. Okay, all right. And so the next step is to define, you know, which parts are going to make up our outputs or make up our objective function. And so to do that, we're going to double click on model. Okay, and we're going to open up ANSYS Mechanical. Right? We also need to make a mesh, and we also need to define our boundary conditions as well. So we'll do that all kind of while we're in here. Okay. All right, so here is our plate, and so it's flat, you know, as like a piece of paper. Okay. And so first thing I want to do here is we're going to define a mesh, and so we don't really need any special settings for this case, and so we're just gonna set a size here. And just to be consistent with the problem document, I'm going to set a mesh size of 5 millimeters. Okay. Let's go ahead and mesh that. And so you should see that this mesh should produce pretty well. And so this is a pretty nice mesh. Okay. And we're going to add a couple boundary conditions as well. Okay. And so first we need to add a fixed constraint. And so, or fixed support, I should say. I should be careful with my terminology today. Okay, so let's go ahead and add a fixed support. And we're going to apply a fixed support on this edge right here. Okay. And so if you're looking at the geometry, then we're going to apply the fixed support on kind of this kind of curved edge on the left right here. Okay. The part is perfectly symmetric. And so, you know, you don't really have to worry about which edge it is. But if you want to do the same thing as me, I basically click on the Z-axis here, And so the x-axis is pointing to the right, the y-axis is pointing up, and I'm constraining the left edge of the part. Okay. Okay. Next, we're going to need to apply a force. So we're going to apply a load. And so I'm going to import input a force load. And I'm going to apply it on this edge of the part. And so if you're looking at it from the same direction, it's going to be the edge on the right. Right. The only thing that you have to make sure of is that the edge should be on the opposite side of wherever you applied the fixed support. Okay. Okay, so let's go ahead and apply that that edge right there. I'm going to define this. I'm going to define this force in terms of its components, and this force is going to be a compressive force, and so it's going to go in the minus x direction, and we're going to give it a magnitude of 5,000 newtons. Okay. And so you should have two boundary conditions here. So you should have a fixed support here on the left, and then a compressive force of 5,000 newtons pushing into the plate.
Professor, quick question. Was the mesh size 5 millimeters or 5 meters?
5 millimeters.
Thank you.
Yeah, so a mesh of 5 millimeters, one fixed support, and one compressive force. All right, anyone have questions on this? Okay. All right, so let's go ahead and run the simulation. And so we're going to add a total deformation field as well as an equivalent stress field. Okay. So let's go ahead and solve. Should finish up very quickly. Okay. Go ahead and erase these lines. Okay. And so you should get an equivalent stress field that looks like this, and a total deformation field that looks like that. Okay. All right, was everyone able to get this deformation field? So you should get a total a max deformation of about 0.036 millimeters. And then your maximum equivalent stress should be about 95.2 megapascal. Okay. Anyone have questions on this part? Question in the chat. Okay, good. Okay. All right. So now that we've run the simulation, we need to specify which variables are going to be the outputs of our optimization. Okay. And so remember, the way that the optimization works is that, ANSYS is going to tinker with the design variable. So we've already set the design variables, and then it's going to run simulations on this, and then it's going to check the results in terms of whichever we define as the outputs. Okay. We basically have to tell ANSYS, what should it be looking for? What should it be optimizing over? Okay. And so we're going to specify two things as outputs here. And so the first thing we're going to specify is the maximum deformation. Okay. And so you're going to click on total deformation here from your outputs field, and you're going to go to the lower left-hand side of the screen. And so you should see kind of a section of this called results. Right, and so the results here should tell you the minimum deformation, it should tell you the maximum deformation, as well as the average deformation. Okay? And so for this activity here, we're going to optimize over the maximum deformation. We want to basically minimize the amount of deformation that we have. Okay? And so just like before, I'm going to click on the checkbox next to maximum, and so there should be a P next to that. Okay. And then the next thing we're going to set here is that we also want to save on cost. And so the way that we're going to save on cost is we're going to say that, we want to optimize over the mass of the geometry. Okay. And so we want to reduce the amount of mass as much as possible. So this is a very common thing in optimization, because a lot of times when you're optimizing things, you want to save material costs, you want to save manufacturing costs. Okay. Okay. And so you're going to click on geometry over here. Okay. So click on geometry. And so of course that's going to change the details window in the bottom left. Okay. You're going to click on properties. And then the other thing that we're going to set as a parameter here is the mass. Okay. So make sure you click on that as well. Okay. So we've set two outputs here. So we've set the maximum deformation as an output, and we've also set the parts mass as an output as well. Okay. Okay. Any questions on this? Okay, so now that we have our design variables, now that we have our outputs, we can go ahead and set up the optimization. Okay, so go ahead and close mechanical. And so believe it or not, we don't need that anymore today, even though we spend most of our time there. Okay. And so now let's go back to ANSYS workbench. And so, where we're going to spend the majority of our time here is going to be on this box right here called parameter set. Okay, so let's go ahead and double click on parameter set. And that's going to bring up this new window right here, okay, which shows you everything that we've marked as P. And so for the input parameters for our design variables, you can see that we have the width and we have the fillet radius. Okay, so those are the things we set in design modeler. And then for the output variables, we set the total deformation maximum and the geometry mass as outputs as well. Okay. Okay. All right, and so okay. And so now that we've kind of checked the parameters here, now we need to set an optimization. Okay, so let's go ahead and close this parameter set. And so we're back on workbench right here. And so now we're going to add a new object here from the left-hand side from the toolbox. Okay. Okay. And so it's actually not going to be from our usual analysis systems. And so we're going to scroll down. Okay. And so go to the toolbox and scroll down. And what you're going to do is you're going to go under design exploration. And then we're gonna use this tool right here called direct optimization. Okay. And so once you found direct optimization, you can go ahead and double click it. And so since we only have one parameter set here, it should directly associate with that parameter set. Okay. And so, make sure you double click on direct optimization and make sure it's associated with that. Okay. And then once you've done that, you can go ahead and double click on this optimization right here. Okay. Okay, so was everyone able to get to this menu right here by setting a direct optimization for that? Okay. Okay. So I kind of lied earlier. So actually, we're going to spend most of our time here, not inside the parameter set. Okay. Okay, and so first thing we're going to do here is, if you'll notice here, we have a question mark next to optimization. And so that tells us we need to set something there. So let's go ahead and left click on that once. And so after you left click on that, we are going to set some parameters here in the bottom middle of the screen. Okay. Okay, so there's a lot of different settings here, but luckily we only have to change a couple. Okay. And so the main things that we are going to investigate are these two parameters right here. Okay? And so first being the method selection and the other being the runtime index. Okay? So let's look at method selection first. Okay. Oops. Do that. Okay. And so for method selection, this is basically, your way of specifying, which optimization method that ANSYS is going to use. So we talked about this kind of at the very end of lecture on Monday. So there are different optimization methods out there that are used to kind of run an optimization. Okay. And so if you wanted some control over which method that you're using, maybe the auto method is not really performing well, you can make that change here. And so you would basically change this to manual. Okay. And then you would change the method here. Okay. So you can see there's a few different methods here. One of which is kind of dangerously named MOGA, close to something else that is not savory. But you can see that there's multiple stuff here. Okay. Why is it doing that? But for now, we're just going to keep it on auto, and so we're going to let ANSYS kind of choose its own thing. Okay. But if you did want to experiment with different methods, that's basically how you would do it. Okay. Okay. But the main thing that we're going to change here is this time index. Okay. And so from this time index, you can change, how quickly or how long you want to run your optimization. Okay. And so you can see here that it gives you various scores here from 1 to 9. Okay. And so the difference here is that, for 1, 1 is a very quick optimization. And so that's one that's going to finish very quickly, but it may not give you the most optimal solution. Okay. And so it's basically just going to do a quick search, and then it's going to give you the best results from that quick search. And so it may not be truly off. Okay. On the other side of the spectrum is a 9. And so a 9 is going to be a long search. So that's going to be a very thorough search. And so that's going to take a very long time. But what you get from this is that, if you use a 9 for this, you're pretty confident that the result that you get is going to be very, very optimal. And so, that's if you have a lot of time on your hand and you really want to make sure you get the right solution. Okay. Where we're going to be for this activity, just to make sure that we finish in time, before the end of class, is we're going to be at a 2, actually. Okay. And so I tried this out with various different parameters, and I waited a very long time. But the one that kind of works best for an in-class setting is 2. Right. And so, of course, with only a 2, we're not going to be very confident that the result that we get is actually truly optimal. But we only have 75 minutes in a class, and so we have to go with that. But when you're trying this on your own, definitely experiment with this and see, if you raise this up to a 3 or 4 or 5. Or even a 9, you can see how long it takes. Okay? A fun experiment would be to set it to 9, right before you go to bed, and then wake up the next day and see if it's finished or not. And believe it or not, that's not an easy question to answer. It may be done. It may only be 20% done. You don't know, and so it depends on your computer. Okay, but we'll go ahead and set that to 2. And then, we'll go from there. Okay. All right. Any questions on this part here? Okay. All right. And so our next destination here is going to be objectives and constraints. And so let's go ahead and click on that. Okay. And so if you click on objectives and constraints, then you're going to see a new window here pop up on the right. Okay. Okay. And so from here, we're going to define, how ANSYS should treat each of the outputs and each of the design variables of our optimization. Okay. And so if you click, why does it keep doing that? Okay. And so if you click on this down arrow right here, under select a parameter, you should see all of the parameters that we've chosen, that we've selected so far, right? And so first we have our input variables. And so we have the width and the fillet radius, and then we have the outputs here. Total deformation maximum and the geometry mass. Okay. And so from here, we're basically going to tell ANSYS kind of what it should do for each case. Okay. So let's go with our outputs first. And so let's go ahead and start with total deformation maximum. Okay. Right. And so now we're going to tell ANSYS, what it should do with this. Okay. So what should it be optimizing? And so for this optimization, we want to minimize this as much as possible. Okay, so we want to basically minimize the amount of deformation that we get. Okay, and so you're going to select minimize under type right here. Okay, and we're not going to constrain this, and so we're just going to leave it as it is. Okay. Okay. The next thing that we're going to optimize over is the mass, and so go ahead and click on mass for the next parameter. And then just like the previous one, we want to minimize the mass. So we want to find a design that has the minimal amount of mass possible. But that's because that's going to be the minimal amount of cost that's going to take to run the simulation or to create the part. Okay. And so we're going to add one additional thing for the mass. And so we're going to add an upper bound. Okay. And so on the right here, you should see a box here for constraint. Okay. And so we're going to add an upper bound constraint. And so what that is telling ANSYS is that we want to make it so that the mass does not exceed a certain number. And that number for our optimization is going to be 0.275. All right. And so basically we're telling ANSYS that no matter what you pick for the design, the mass should not exceed 0.275. Yeah, question.
Dr. Chan,
Sorry, I mean, there's a question in the class first. I'll come back to you. Yeah.
The unit, would you be able to change it like easily
For this? Oh, yes, yeah. So this assumes kind of the default kind of units for the whatever you left on ANSYS mechanical. Yeah, from the model. And so if you change the units there, it's going to change the units
So you
here.
have to go back.
Yeah. Yeah, that's usually the best way to do this. All right, Ivan, question?
Where did you get that value from? That 0.275?
Nothing special. I mean, this is just an activity, and so it was something that gives us kind of interesting results for this optimization. But it doesn't. But this part also doesn't really have any physical significance.
So where would an engineer? Does the engineer just set that to some low number, or?
Yeah, so normally, if you're running this optimization in practice, you would get that number based on the design constraints that you're given for the part in general. And so, maybe you're designing a part that's going to be mass produced. And so, your boss is telling you that, you have to produce this part, with less than, $5 or something like that. And so based on the cost of materials, based on the manufacturing costs, based on, all those things, then from there you could compute, what the maximum amount of mass that you can have for this part and still satisfy that cost constraint. Yeah.
I see. Thank you, sir.
Yeah. Mhm. All right, any other questions on this part here? Okay. All right, so those are the outputs. And so now ANSYS knows what to do for those. So it wants to minimize these with an upper bound for the mass. Okay. Now let's work on our input parameters. And so we have the width and we have our fillet radius. Okay. 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 And so for these ones, we're actually not gonna put any objectives here. Okay. Instead, we're going to put the objective somewhere else. Okay.
Professor, real quick, the H4 was the width, right? And the okay, thank you. I left it a default name, that's why.
Okay, yeah, H4 is the width, and then the R5 is the fillet radius.
Thank you.
Yep. Okay. And so next thing we're going to do is we need to constrain our input parameters. And so to do that, we're going to click on static structural A1 on the left right here. Okay. And so once you click that, it'll show you your two input parameters here. Okay. And here we're looking at our constraints. And so for the width here, we can see we have a lower bound of 27 and an upper bound of 33. And for a fillet radius, we have a lower bound of 9 and an upper bound of 11. Okay. So these are the default constraints. And you can see that, the way ANSYS selected these is that it just chose, plus or minus 10% over the default values, right? And so for the width, our default value is 30, and for the fillet radius, our default value is 10, and so it just went plus or minus 10% on that. Okay. Okay, but for this optimization, we're going to increase these widths, okay, or increase the bounds. And so for the lower bound for the width, we're going to set this equal to 25. Okay. And for the upper bound for the width, we're going to set this equal to 35. For the fillet radius, for the lower bound, we're going to set this equal to 8. And then for the upper bound, we're going to set this equal to 12. Okay. And so now, now we're basically telling ANSYS to, expand your search. And so, search over more parameters because we've relaxed the constraints. Okay. Okay. And actually, let me go ahead and delete these P1, P2, just so that it doesn't get confused. Okay. And so under objectives and constraints, if you added the P1, P2 here, just go ahead and delete them. I was kind of skipping ahead in the notes a little bit. Actually, we set the constraints here. So there's no need to set the constraints under objectives and constraints because these are purely just for the objectives. And then for the design parameters, we set them here under static structure. Okay. And so in the end, you should have a kind of a left-hand side tree that looks like this. So under objectives and constraints, you should have two entries. And so you should have minimize P3, minimize P4, with P4 being less than or equal to 0.275. And then under static structural, you should have a lower bound of 25 and an upper bound of 35 for the width. And then the fillet radius should go between 8 and 12. Okay. Any questions on this here? Okay. Okay, so let's go ahead and clear this. And so we're just about ready to run the optimization. Okay. And so let's go ahead and click back here. And so I'm going to click on optimization again. And I'm going to increase the width of this table just so it's not as annoying to read. Okay. And so I clicked on optimization. You can see now that it has a green check mark, or excuse me, a yellow lightning bolt. And so that tells us that it's ready to go. Okay. But before we start, I want you to take notice of this line right here. So line 9. Okay. And so this line 9 tells you approximately how many simulations that ANSYS thinks it needs to run in order to complete this optimization. Okay. And so under the current settings, under the current constraints, and under the current runtime index, ANSYS thinks that it's going to take 40 simulations in order to run. Okay. So let's change this runtime index and see how the simulations is going to change. And so if we change this runtime index to 3, it's going to take 59 simulations. If we change it up to 7, it's going to be 136. And then, the worst case is going to be 192 simulations. But that's going to take a very long time. So let's go ahead and change it back to 2 and run the optimization. Okay. Okay, so once you're ready, you're going to go to the upper left-hand side of the screen. You're going to click Update. Okay. And so this is going to start the optimization process. Right? So let's go ahead and click that. Okay, and so now the optimization it's going to start running. Okay. Okay. And so now we sit and we wait, and we're going to wait for a very long time. But if you want to check and see how the optimization is going, you can check on this table in the top right here. Okay, so I know the activity is a little bit annoying here. You have to kind of click and drag these windows around a lot. Okay. But what this table is showing you is that this is showing you all the different design points that the optimization is trying. Okay. And so if you scroll down this table, you can see here we have 40 points. Okay. And each row here is a different simulation. Okay. All right. And so you can see your simulation kind of completing in real time. And so for this
Can I ask a question, Dr. Sean?
Oh, sure. Yes. Sorry.
Is there a relationship between the number of simulations and accuracy? The more simulations, the more accurate, or is it just the more simulations, meaning it's complicated for the computer?
Yeah, no, we discussed that before. So the number of simulations that you set is based on the runtime index. And so the more simulations that you run, you're going to get a more optimal result.
Okay, sounds good.
Yeah, so you can almost think of it as this is not the best analogy, but you can almost think of it like throwing darts at a board, right? And so if you have 40 darts, and basically you're being asked to hit the bullseye within 40 darts, you might hit it, but if you had 200 darts, you're going to be much more likely to hit the center because you have more tries going at it.
I see. Sounds good, sir.
Yeah,
I apologize if I'm asking redundant questions. I'm just asking just to make sure there's no hesitation on my end.
Oh yeah, no, it's a good question. So it's definitely good to ask to clarify these things.
Better to be safe than sorry, right? Especially as engineers.
Exactly, right.
It sounds good, sir.
Yep. Yeah. And so what you should be seeing here is that your results are updating in real time. So each row here is a separate simulation. So the first simulation we're using a width of 25.125 and a fillet radius of 8.05, and these are the results. Okay. And so we get a total deformation of 0.46 and a mass of 0.196. And then what it's doing from here is that, for all the different parameter sets, it's changing the geometry, it's remeshing it, it's reapplying the boundary conditions and running the simulations and tracking what you get for the results. Okay. Okay. And so from here, unfortunately, there's not much we can talk about except for it to wait. And so, at this point, if anyone's having some issues getting to this point, I'll go ahead and come around and answer questions, or we can just kind of hang out until then.
I have a question, Professor.
Sure, go ahead, Chris.
So under objectives and constraints,
Yep.
P1 and P2, I kind of got distracted. I didn't see what you did with those two.
Yeah, so I kind of made a mistake. So I thought that we would place the constraints on P1, P2 under objectives and constraints, but we actually put them later. So you can go ahead and delete them. I think if you leave them there with no constraints or no objective, I think it shouldn't change anything either. But just for cleanliness, I just kind of deleted them from objectives and constraints. And I set those constraints under static structural A1.
Okay.
Yeah. Mhm. All right, Bob, questions? So are we supposed to get the same results since the numbers are being picked randomly? No, so actually, so your guys' results might be different than mine because, I think usually for the first part of an optimization, the computer chooses semi-randomly, and so you might get different parts here, but that's okay. And so if you get different design points, that's totally fine. And we might get different results in the end. But the idea is that, across 40 different simulations, we should hopefully get something that's roughly the same or roughly optimal at the very end. Yeah. Okay.
Yes, so I noticed that while you were meshing it, the method, why we just got two options, that was triangle and quadratic. Why is that? What happened to the other one?
Because this is a shell mesh, so it's only 2D, and so you only have triangles and quadrilaterals. If this were a 3D part, you have the hexagon and weave, all that stuff. But I changed this geometry to just a 2D shell, just to make the simulations faster. If this were a 3D simulation, it would take longer. So let's see where we're at. We've completed 8 simulations, so we are 20% done. Yeah, I tried to time it, and so I tried to time my talking so that it should hopefully finish at about the same time that lecture finishes.
Dr. Chan, no one in the class has any inquiries?
Not right now, no.
Okay, then might as well just ask you right now.
Sure.
So, we're doing assignment number 6.
Correct.
Assignment number 7 is going to be released in about 2 weeks, or
Yes.
or-
Yeah,
and
assignment 7 is going to be in 2 weeks from now. Yeah.
that sounds good. So then assignment 8 is going to be in 3 weeks.
Yes, assignment 8. So 5 and 6 are back to back, and then 7 and 8 are back to back. And so we have 1 week in between 6 and 7. And then the final week, I actually don't have anything planned because the final week I don't want to reserve for kind of just workshop for your final.
Yeah, the final week is usually review of the semester.
Yeah. So we don't have any, I'm not gonna do any review, but then, if you want to come in and get kind of one-on-one help on your project, I'm reserving the last 2 days of class. For
Oh,
that.
very nice.
Yeah.
I do have, it just left my head. Okay, so, I got it. In the beginning of the semester, you said that you may make an assignment optional, and that assignment being assignment 8. Are you gonna do that or no?
I probably will, just because, I know that time is going to be crunch time for the final project. I know you guys have other classes too.
Or
So
you could also make it extra credit, and some of us will still do it.
Yeah, I'll probably make it extra credit. Assignment 8 is very short though. It's not very long at all. And so I'll probably make it extra credit, like maybe like 20 homework points or something.
Sounds good, sir.
Yep.
Thank you. I think that's all the questions I had for the class.
Yep. Our question got an error row 5. Yeah, so actually that's a good question. So there's a question in the chat that says, you may get an error on some simulations here. That's okay. And so that can happen sometimes when you're kind of like, when the computer is kind of randomly changing the parameters. You may get a situation where, either the mesh fails to form or, or the simulation kind of blows up, or you might get a pivot warning or something like that. That's kind of the risk that you run when you're doing such a wide search like this. That's okay. And so if it's only a couple times, that's fine. What's gonna happen is that ANSYS is just going to ignore those simulations. Yeah. If it's happening a lot, then yes, that's a cause for concern. But if it's just 1 or 2, that's okay.
Professor, I have a quick question.
Sure. What's up?
So it's kind of, I don't think it's within the scope of the class. However, so in terms of like variation, what if you're trying to optimize a part, however, the overall shape should remain the same? Like in terms of like topology, whether it's mass reduction.
Yeah. Oh, it's a good question. So you're asking, how do you set up that kind of optimization? Oh,
Yes.
okay. Yeah, so it's challenging, yeah. And so, if there's a lot of times, like a lot of the constraints that you have and a lot of the things that you want to achieve are kind of more higher level stuff than just, than just the mass, or minimize the total deformation, or, put constraints on these dimensions, right? And so what you can do, let me see if I can still do it when optimization is running. Yeah, so another way that you can kind of specify, to make sure that your overall shape stays the same, is that you could specify relationships between parameters as well. And so, right now, basically ANSYS is basically it's basically randomly choosing values for these two parameters completely unrelated to each other. So the shape of the part, of course, are going to be somewhat random. But, if you want to preserve the shape, and in order to preserve that shape, certain parameters have to be related. And so, if you cut down this parameter by maybe 20%, then the other parameter also has to be cut down by 20%. You can specify those relationships here in the optimization. Yeah. And so, for a more practical case, it's going to be more complicated than just setting, one or two relationships. So oftentimes you have to set a lot, but that's basically how you do it. Yeah.
Thank you.
Does that answer your question, Amit?
Yes, sir.
Okay, good. Let's see what 17. Actually, it's going pretty fast, so we'll be done before we'll be done before 8 o'clock for sure. All these staples. Every day I come here, there's like more just random staples that are just lying around.
Dr. Chan, I have a question regarding this.
Sure.
Let's say, is it possible for the software to get stuck in a loop? And how would the user know? Because say we're waiting right now, and what if it's in a loop and we just don't know it? Worst case scenario, I'm not doubting your work. I'm just wondering, how would a user know if it's in a loop, and how would they go about?
Yeah, no, it's a good question. And so, you can monitor the optimization in real time. And so, that's kind of what I'm looking at right now.
Oh, I see.
And so, one thing that you can check is to make sure that this table is being continually updated. And so if it's still finishing simulation, then it should be, it'll still be churning. And so if you ever reach a point where, you waited a while.
Just stay stuck for like an hour.
Yeah, so if it gets stuck on a particular simulation and it's not finishing, it could be that, maybe it's having trouble with the mesh and it's trying to simulate it. Because remember, essentially what you're doing here is that you're changing the geometry and you're applying the same mesh settings to every geometry.
I see.
But that might be dangerous, because if you make a change to the geometry such that, maybe you create a very sharp corner or maybe sharp edge, and the mesher has a really hard time meshing in that kind of area, you may end up with a situation where your mesh just totally blows up, right? And so your number of
now
elements.
now I have two more questions.
Sure.
Would the engineer be able to how do I word this without sounding too not intelligent? Would the engineer be able to modify the simulation while it's running at the same time? No, huh? It's gonna corrupt the simulation because it's obviously being edited.
Right. So because it's all automated, basically it's already taken all the settings and applied it, to all of these.
So we cannot do any more edits while it's doing the actual simulation.
Right, right. And
I
that,
see.
and there's a reason for that too, because you don't want to, you also don't want to change any simulation settings midway through, because then it's going to kind of invalidate everything you did before that. So
Yeah,
let's say that
yeah,
you
yeah,
change the
I
mesh.
see. I
And so
agree.
now you have half your results that are on one mesh setting and the other one's on the other mesh setting, and you can't really compare those apples to apples. You know what I mean?
I see, I see. So having said all that, when an engineer runs FEA, do they usually have to be on standby next to the computer, making sure the simulation is okay, or
No, definitely not.
is it common for engineers to just run a simulation and check back the next day to see how
Yeah.
everything went?
I mean, of course, it depends on how long it takes. I mean, something
Yes,
like this,
yes.
which is only taking us maybe, it's gonna probably take us about 20 minutes. This
Mhm.
is usually okay just to kind of stand by and maybe answer emails
Yes, yes.
while you're waiting for this. But for a lot of optimizations, especially kind of practical ones, those are going to
Yeah,
take
it's not
hours.
feasible to like be on
And-
standby for 24 hours.
Exactly
So-
right. So that's not practical at all. And so that's something that you would let it run. You'd either go home for the day or maybe go to a meeting or something like that, and then just check back on it just periodically as much as
I
you
see,
can.
I see.
And then if it fails, then it fails, and you just kind of you modify it again and run it again.
I see, I see. Sounds good, sir. Thank you so much.
Question in the chat. Let's see. Regarding optimization, is there some sort of license restrictions we should be aware of? Something like the element cap? I don't think that there's any cap on the number of simulations you can do with the optimization, but it still is subject to the element cap. And so I think one thing that could happen is that maybe your original mesh, you're kind of skirting very close to that element cap. So let's say that you're at 60,000 elements or something like that. And so it could be that when the optimizer changes the number of or changes the dimensions of your part, and it applies the same mesh settings, it may push your mesh above that threshold. And so it may push, for a particular simulation. So one particular design point, you may have 70,000 elements of mesh, and then ANSYS will say, no, you can't do that. And so, because of the license restrictions. But in terms of the amount of design points, I don't think there's a restriction on that. So you can run it for hundreds or thousands of design points. Although I haven't really pushed it all that much. And so, yeah, I've done up to 200 points just when I was doing my testing for this activity. And that seemed to work okay. I mean, it ran for hours, but it didn't stop me. But I haven't pushed it to like over 1,000 or anything like that. So I haven't really pushed it, but I'm not aware of any restrictions for that.
Dr. Chan.
Yep.
Do you have any memorable FEA simulations that stick out to you in your experience? And why was it so unforgettable?
Yeah, that's a good question. I never really thought about that. I guess when I was at the tail end of grad school, I was working on a project. It didn't end up going anywhere. I thought it ended up somewhere, but my advisor said this is nowhere. So it went nowhere. But I was working on developing code to do fluid. It's called fluid structure interaction. So
In what language?
wait a second.
In what language?
Fortran.
Oh, Fortran.
And so basically that's because a lot of my grad school research was based on blood vessels. And so I was working on a code to basically simulate the fact that blood vessels are flexible and they kind of react to the pressures in your cardiovascular system. So when the pressure is high, the blood vessels expand, and when it's low, it kind of contracts. And so I was working on a code that kind of worked on that. And so I got some interesting results. I got some simulations that kind of breathe, but it wasn't at a point where we could publish it. And so, but that was cool. That was probably the most hands-on I've ever been in terms of developing FEA code. And I just kind of wish I had more time to work on it before I graduated.
Which FBA software uses Fortran?
It was our own homebrew software, so it was one that we
I
developed.
see.
Yeah.
And what university was this at?
This was at Stanford.
Oh, very nice. Yeah, I was just wondering. Sounds good, sir.
Yep. Let's see how we're doing. Almost there. 3 more simulations. Oh, question in the chat. Let's see. 4 errors. Yeah, four errors is fine. Yeah, don't worry about 4 errors. What games am I playing now on my PC? I've actually been playing my Switch recently. So I got the new Fire Emblem game, Fire Emblem Engage. So I've been playing that one a lot. Yeah, not much I'm playing on PC right
Dr. Chan.
Yep.
During my undergrad, my undergrad's in structural engineering, so we had to do FEA.
Yep.
Not civil engineering, structural engineering.
Sure.
So there's a difference. I'm just putting that out there.
Sure.
Because everyone thinks structural engineering falls within civil engineering. But I digress. So, but at my during my undergrad, the university I was at, they were using Abacus. Is there a reason? Do you have any? What's your opinion on Abacus? And why don't we use it here at CSUF? Now, from my understanding, Abacus is more for the it's more research oriented, and ANSYS is for more industry oriented. Is that why?
Yeah, no, that's right. Yeah, so that's typically, I would say that's more just based on the audiences that typically use them. And so Abacus, you're right, is used more in research labs, and ANSYS is more used in industry. I like Abacus. I've only used it a few times, but I know it's well respected. I know it gives you good stuff. And so the reason I use ANSYS here is because when I started working here, there's already a relationship between the ANSYS company and Cal State Fullerton. And there wasn't such a relationship between Abacus and Cal State Fullerton.
Yeah, when I first started with Abacus, it was very difficult because there's not a lot of resources online as there are with the ANSYS. There's a lot
Right.
more resources for ANSYS as
Yeah.
for a student. So it was very frustrating, but thank you
Yeah,
for your
Abacus
input.
is mostly taught, the way I understand it is that a lot of the research labs that use Abacus, they have their own internal documentation about how they use it. And of
I
course, that
see.
doesn't really get shared around all that much. But
Yeah,
ANSYS has done a lot more. ANSYS, the company, has done a much better job in terms of like educating its user base.
Yeah, it's a lot more user friendly. ANSYS.
Yeah, no,
I
I
remember
agree with that.
installing Abacus was very, very difficult. That was an activity on its own.
Yeah, yeah. I know there was another faculty here that tried to get an Abacus license for our school. But it ended up just not really going anywhere just because the school didn't want to pay for it and Abacus wasn't really, willing to give us a discount. And so it was a very difficult process. And so ANSYS was kind of the least activation energy required to kind of get started. It's interesting though, because like before I started working here, I'd never used ANSYS. And so I learned it kind of on the fly while I was teaching the course, which was a very interesting
what
experience.
software did you use then? Were you using Abacus or
Wait, say again?
which software were you using before you came here? If that's the
Oh,
case.
it was our homebrew software. So just
I see. Oh yeah,
one that
yeah.
we developed
You
in
mentioned
lab.
that. You mentioned that.
Yeah.
I see.
Okay, all right. So my optimization is done. So your guys' might still be going depending on how strong your computer is. But for the last 15 minutes today, I kind of want to show you a little bit of how to look at the results. Okay. And so to view the best results, and so you can look and see, these are the 40 points that we simulated. And so ANSYS has already automatically going to select the 3 best results to show. Okay, and so if you click on candidate points right here, it's going to show you the 3 best results. And so the best result here had a width of 28.875. It had a fillet radius of almost 12. And it had these deformations here and this mass. And so remember, we're trying to optimize 2 things at the same time. And so even though these 3 points are different, they're going to give you 3 different results in terms of the total deformation and the mass. And so maybe one result might be better for the deformation. And so in this case, the candidate point 1 gave us the best deformation. The other 2 points gave us a larger deformation. But the other 2 points are slightly better for the mass right here. So there's no, sometimes you'll get a result with the clear-cut winner. And here, because it was a fairly complicated optimization, it wasn't that complicated. It's just we chose 2 outputs here that were kind of conflicting with each other. And so you're going to get kind of a gray area solution. And so you can choose which one that you like the best. And so and so ANSYS has chosen this one as the best one because this one had the best the best deformation value. But maybe if you really want to optimize over the mass, maybe you'll click candidate point 2. And that's kind of what you would do. That's what you would pick. Okay. And so you can go ahead and experiment with this. And so one thing that you can do is you can kind of insert this as a candidate point. Another thing that you can do is that you can run your simulation with these parameter values just to kind of make sure that you get these same results. Okay, so let's try that. So let's go ahead and right click this and insert it as a design point. And so if you go back here, let's see, how do we do this again? Examples, trade-off. There is a way that you can kind of automatically load this into ANSYS Workbench and then try a simulation with it. My own documentation was not very good with this. Parameter set. Okay, here we go. Okay, and so to see this to see that design point, and so basically remember what I did was I looked at our candidate points here. I right click on candidate point 1 and I inserted it as a design point. And if you go back to Workbench, or if you go back to the problem schematic and you double click on parameter set, If you go on the right, you should see that there is one design point right here, okay? And that was our most optimal design. So what you can do is you can right click this and you can copy the inputs to current. Okay? And then what that's going to do is that it's going to change your geometry so that it matches those design points. Okay? And so now if you go back into geometry here, okay, you'll see that the values for those dimensions should update to whatever you set your design to. Okay. And so if we go to this, if we go to the sketch right here, you can see that our values for H4 and R5, they've changed to what our design point was, which was 28.875 for the width, and then 11.8 for the fill radius. Okay. And again, probably for you guys, because the points were chosen somewhat randomly, you may get different results than these, and that's okay. So you may get a different optimal point, but this is how you would kind of try it. And what you would do is you'd click generate. Okay, and so that would change the geometry. Okay. And then you would go back into model right here, and you would rerun the simulation to show you the results. Okay. Okay. Let's go and click solve. And so now our geometry is updated. It doesn't look like it just because we've only been making small changes to the geometry, but this is with the updated dimensions. Okay. And so if you look at the total deformation, we can see that the maximum total deformation is only 0.368. And so that's what it was from the optimization. And if you look at the mass, the mass is 0.21451. Okay. Okay, and so if you wanted to try out your optimal parameters and you wanted to check the other simulation results like the equivalent stress or something like that, that's basically how you would do it. So just to kind of recap, you would go to the optimization here, you would go to your candidate points, you'd right click on the candidate point that you want to test out, you'd click on insert as design point, okay? And then what that's going to do is that it's going to insert this design point here onto your table of design points once you double click on parameter set here. Okay. And then what you would do is that you would copy the inputs to current, and then you would regenerate the geometry, you'd rerun the simulations, and then you can check basically everything else. Okay, so I think I have you doing that as part of the other parts of the activity, so that's definitely useful. Okay. Any questions on that part there? Okay. All right, so for the last 10 minutes of class today, let's go over the last parts of the activity. So I'm having you do a few more things just to test things out. But that's kind of, that's basically how you run a simulation from front to back. So that gets you through problem 4 on the homework. Okay. But there are 3 more big problems that I want you to do. Okay. So problem 5, I want you to change the outputs. So I want you to rerun the optimization, but I want you to change at least one of the outputs for the optimization. Okay? And so for the initial optimization, we had 2 outputs. We had the geometry's mass as well as the maximum total deformation. And so you can change the total deformation to stress. You can just even add the stress to the optimization, or maybe you can do something else. And so maybe you can do like the maybe like the strain or something like that, or maybe something like a directional stress, like a normal stress. Okay? And so I want you to basically change the outputs, rerun the optimization, and then show me what you get for the results. Okay. Okay, problem 6, I want you to try changing the loading. And so I want you to rerun the optimization, but change the loading configuration. Okay? And so the loading for this one that we chose was fairly simple. And so we had just a single fixed support and a single compressive force. Right? And so I want you to change that. And so maybe instead of compressive force, maybe you put a shearing force. Okay. You can try a tensile force, but I don't think you're going to see much differences with a tensile force. Or maybe you're going to put an internal force on this internal triangle right here. Okay. Or maybe you put a force kind of on these curved edges. You can be creative. And so I want you to change the loading. And then I want you to rerun the optimization and again, kind of show me what you get. Okay, so it's going to change your results because your results are dependent on the loading. Okay, And then for problem 7, this one's going to take you a while because this one I want you to increase the amount of input parameters. Okay. And so I want you to rerun the optimization, but I want you to choose one additional input parameter. Okay. So you're going to open up Design Modeler. You're going to choose one additional dimension that's there. So there are 5 total that's given to you in that Design Modeler. So choose one more, rerun the optimization with 3 design inputs, and then show me what you get. Okay? So of course, because we're increasing the amount of inputs, this is going to increase the cost of your optimization. So make sure you set aside enough time for doing this. Okay, and then finally, problem 8 is just summarizing your findings. So just like usual. Okay. Okay, so there's quite a lot to do. It is going to take a lot of time, but a lot of the time is going to be hands off. And so you're basically I'm having you set up 3 different optimizations. And I want you to let them go. But remember, you don't have to babysit it. You don't have to kind of be there to kind of watch the optimization. You can kind of just set it and leave. Okay. All right. Any final questions on the activity before we wrap it up for today? Okay. All right. So we have about 5 more minutes, and so I'll stick around until the end of class. And so if you're still working on something, if you have questions, I'll stick around to answer questions. But if not, that's all I got for today. So thank you guys for coming today as usual. So hope you guys enjoy your weekend, and I will see you guys next week.
Thank you, Dr. Tron.
Thanks, Ivan. Have a good weekend.
You too, sir.
Thank you, Professor.
Thanks, Ismail. Have a good weekend.
You too.